So in this lesson, we're going to talk about Ohm's law, and then we'll talk about just a qualitative analysis of circuits. We won't get into actually calculating anything with circuits. So Ohm's law says that the current in a circuit is equal to the potential difference over the resistance. And current, that would be volts per ohm. But we also know that it's just amps. So this is the relationship between it. Now if we graph the current versus potential difference for three different resistors, we get these three different graphs. And what Ohm's law tells us, if I rearrange this so that it looks more like a, let me change colors. So I would be 1 over R delta V. And so if I'm graphing this versus this, then the slope would be 1 over R. And so we can tell something about the resistance here. Now the resistance is its inverse. And so this would indicate that R1 is greater than R2 because I have a smaller slope. And when I divide by a smaller number, I get a bigger number here, or a smaller number. Bigger number, this becomes smaller, so I get less resistance. I totally misspoke. Okay. The slope is smaller, so this number has to be bigger. So R1 has to be bigger. Basically, you'll get less current with greater resistance. This other one up here, because it's not a line, so if it's non-linear, this is called a non-ohmic resistor. Non-ohmic resistor. These two are called ohmic. And all it means is that the circuit is obeying Ohm's law. This one is not. It's doing something else. We won't analyze these in this course. We just refer to it as non-ohmic. So if you want to know if a resistor is ohmic, you just plot it and you see if it's a line. If it's linear, it's ohmic. And that's Ohm's law. All right, qualitative analysis of circuits. So one thing we can do is we can think about a circuit by the potential as a charge moves along the circuit, and we can graph it accordingly. And the first one I want to do is this one. This should be simple circuits. Basically, we just have a battery connected to the other terminal, and this is called a short circuit. And these are dangerous. These will blow up. And let's think about why. So the battery, remember, takes some charge and it builds up charge on one side. So let's say this goes to 9 volts. So the battery, we're typically start thinking about things at the negative side. Remember, we're talking conventional current flow. So we're not talking about electrons, conventional flow. So we would start at this point A on this side. And so that would be our origin when we would start with 0 potential. And then across the battery to point B, the battery has used a chemical process to create some potential up here. So it goes up here. And now we typically just ignore any resistance in the wire. So if I go along the wire, I can see like at point C, so if I go to point C, my potential is still the same. It hasn't gone anywhere. And then if I come back around to D, it's the same case. So D, it's still way up here. And then what's going to happen is it's going to enter A, and then from A to B, so this is D, and then it goes back to A, and A to B is going to pump it up again. And then it'll go through this cycle, and so we'll end up doing this kind of thing. And so over time, what's going to happen is the potential difference is going to go to infinity, and things blow up. The other way to think about this is with Ohm's law, that the current is the potential difference divided by the resistance. And so as the resistance goes to 0, so as R goes to 0, then this number gets really, really, really small. That means that this whole quantity gets really, really, really big. So I goes to positive infinity. And so we would have an infinite current going through there. So the charge would be flowing fast, 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 fast. And so it would heat up and burn up and catch on fire and blow up and do all sorts of nastiness. The other thing you could think about is basically there's zero resistance. And when you divide by zero, that breaks the universe. So we don't do that. So we never connect this. This is how you'll start a fire pretty easily. You could hurt yourself. So this is the simplest circuit we'll ever construct. This is a battery with a single resistor. And we want to think about the potential. So we'll start here. This will be point A. Then we'll go to B, C, and D. And we're ignoring resistance in the wire. So let's go and label these point A, B, C, D. And then back to A. Okay, so from A to B, the battery pumps it up, so it gives it some potential. So that's point B. And then from B to C, there's no change, so it just moves along, keeps the same potential. So no potential difference between B and C. Across C and D, it's going to drop all the way to zero. And so that when it enters back at A, there's zero potential. And then we repeat the process again. So it would pump back up like this and go like that. That would be a full 2 cycles. That would be 2 cycles through this. Okay. What happens if there's multiple, though? Multiple resistors. And this one actually has a battery. It has 2 batteries, 2 resistors. So let's think about this. I don't know if my graph's going to be big enough. We'll go A, B, C, D, E, F, G, and then back to A. All right. I'm going to have to erase some of this. I have to extend this a little bit. So let's get this way out here so I don't have to worry about it. All right. So from A to B, does the same thing. It's going to pump it up. So that's point B. And the same thing, as it goes around to C, there's no change. So the potential stays the same. And then across C to D, we're not going to lose all of the potential. And the reason for that is over on the other side. So notice this is a 4 volt and this is 8 volt. So we have half the potential over here, and there's another resistor. But anyway, we'll drop, the voltage will drop, but then this thing is going to pump it back up. So it goes from D to E, and then the battery pumps it back up to 8 volts. And then from, so this is E, F. That's when it comes out. And then it goes through the resistor, and now the resistance is going to drop all the way down to 0. And that's point G before it goes back into the battery over here. So you get this you get a pump up somewhere. This indicates that there's a battery. Whenever you see these, whenever it goes up, you have a battery. When it goes down, you have resistors. And the other thing is to know that your potential is 0 at the end. So you'll lose all your potential before you go back into the battery. Okay, let's look at this. So this type of setup. So if we do the potential, again, this is a simple circuit. So the battery will pump it up, then it goes over to the bulb, and then the bulb drops the potential, and then it's back to 0. That's for this one, number 1. But what happens if we put 2 bulbs? So if we put 2 bulbs, and these things have the same resistance, so we'll say R, R, and R. These are all the same. When it gets to this bulb, so it's going to pump it up again. I don't know if I should draw it on the same one. Let's draw a new one. So we'll do VR. All right. So the battery's going to pump it up the same, and then it goes over to the resistor. Now, when it goes across this bulb, it can't lose everything, because it still needs to go across another one. And since these are the same resistor, then it's only going to lose half. So it would lose half of the voltage, go to the new bulb, and then the other bulb would take it away. So what's the net effect here? This one is very bright, and these will be about half as bright. So not as bright. When we connect things like this, one right after another, this is called in series. In series. So when it's one right after another, they're called in series. And we're going to get into all the specifics of it. I'll lay out some groundwork for you, but basically there's a couple things that you're going to need to know. Number one, the current going across these things is the same. The current that goes here has to come out the other side. So for in series, we get the same current. And then the other thing is, when you add a new resistor, that's going to increase the total resistance. And by Ohm's law, if you increase the resistance, then you decrease the current. So when the resistance goes up, the current goes down. So you get less current across them. And so since we have less current, less potential. Or the potential is still the same, but it's just split up amongst these. That's the idea. Okay. The other way that we can set them up are like this. This is called in parallel. And this one's a little trickier to think about. But basically, if we just analyze this little loop, so if you have charge coming up here, it's going to get to this junction. And we're just thinking about one charge. So we just have a positive charge. When it gets here, it decides it's either going to go this way or it's going to go that way. And so what ends up happening is the current that's coming around ends up getting split. And so you'll have let's make this, I'm going to call this 3I, just to make it easy. So when it gets split, we'll have an I go this way. Now it's not always the same. It depends on the resistance. And then we'll get 2I that come up this way. And then when it gets up to this junction, we're going to get the same thing. So we end up getting I here, and we get an I up here. But the idea is that the current is going to split. So across the resistors, we can have different currents. Not always. It's not necessarily the same. But if we think about a charge going, okay, so the charge leaves and it goes across here. So if we think about our graph, it's going to do this type of stuff. So it has potential here. It goes up through here, and when it goes across this resistor, it has to lose all the potential before it comes back in the battery. So the potential here has to be the same as what's right here. Likewise, if it decides to go this way and go over this one, it has to lose all of it before it comes back. Now, when it gets here, it can't go this way. It's got to go back to the battery. So we know that this has the same potential and the same kind of reasoning for the top one. So in parallel, we get the same potential difference, but we can have different current. And this is the weird one. As we add new resistors, the effective resistance of the circuit goes down and the current goes up. This one's a big one. So if your current goes too high, you can blow up the entire circuit. So two different ways, in series and parallel. How do you think your house is wired up? Well, it's actually a combination of both, but this is the overall one. You get these parallel circuits in your house because when the current gets high enough, what happens is you have a circuit breaker in your outside of your house or down in your basement or somewhere. And when the current gets high enough, they're usually like 20 amps, this thing's going to trip and it opens up the circuit. So that all the electricity stops flowing through that circuit because there's too much draw on it. But we'll talk more about this in class. That's the basic idea, though. So to summarize with your in series and in parallel, in series, the current across the elements is the same, whereas in parallel, the potential difference is the same. And then when we add more elements in series, it decreases the current and increases the resistance. In parallel, it increases the current and decreases the resistance. So you need to know this. We're going to get into the quantitative starting next time. We'll start analyzing, and we'll build up with analyzing these kinds of circuits quantitatively.